How does discarded scrap steel become precision machined heavy equipment? The answer lies in thousands of degrees of heat and unyielding mechanical force. Here is how a rusted pile of debris is transformed. The journey of every component here begins in the chaotic heat of the melting furnace. Scrap iron is loaded into the crucible, where temperatures must exceed 2,800 degrees Fahrenheit to break down the metal's solid lattice. At this extreme heat, impurities like rust and dirt separate from the base iron, floating to the surface as slag. The operators use long steel rods to manually aggregate this molten mass, ensuring a homogeneous mixture before the pour. Stirring is critical. Without it, cold spots could form, leading to weak points in the final casting. The process relies heavily on visual cues, with the precise shade of glowing orange indicating when the liquid is ready for the molds. Once the ideal viscosity is reached, the liquid iron must be transferred immediately before ambient air rapidly cools it. The team maneuvers a heavy, glowing crucible suspended between guide rods, relying on coordinated balance to control the pour. Moving this much thermal mass requires extreme care. A single misstep would spill hundreds of pounds of liquid fire. They fill a grid of square sand molds laid directly on the dirt floor. Sand casting is an ancient but highly effective technique, allowing the molds to absorb intense thermal shock without shattering. As the metal fills the voids, it immediately begins to solidify, transitioning from a volatile liquid to a structured crystalline solid. The distinct shift from bright yellow to a dull, dark red indicates the temperature is dropping rapidly. Finally, the solid plates are forcefully broken out of their encasements. What was an unrecognizable pile of scrap just hours ago has now taken its first geometric shape. Raw cast iron is extremely brittle, entirely unsuited for bearing mechanical loads. To change its molecular structure, the freshly cast plates are sent into a secondary annealing furnace. This controlled reheat brings the metal just below its melting point, increasing its plasticity so it can be shaped without fracturing. Once it reaches a uniform bright orange, the plate is fed into a massive industrial rolling mill. Heavy steel rollers compress the thick plate under immense pressure, stretching its grain structure along a single axis. This physical deformation is known as work hardening. It drastically increases the tensile strength of the material while reducing its overall thickness. The mill operators guide the steel back and forth, tightening the gap between the rollers with each pass to achieve the precise final gauge. It takes immense torque to flatten solid steel, and the machine exerts tremendous downward force to force the metal into compliance. The rapid heat loss during rolling means they must work continuously, as cooling steel quickly becomes too stubborn to form. The elongated plates are marked for quality control and sorted by dimension. Even in a heavy industrial setting, strict weight tolerances must be maintained to ensure consistency in the next manufacturing stage. The technicians verify the mass of each piece on a mechanical scale, rejecting any plates that fall outside the specified range. These standardized blanks are then loaded up, ready to be machined into their final complex shapes. Not all material requires wide, flat pressing. For narrower profiles, glowing bar stock is fed through a specialized rolling die. The operators rely on heavy iron tongs to maintain their grip, fighting both the intense radiated heat and the violent mechanical pull of the machine. The rollers squeeze the profile into a tight, dense ribbon of steel, aligning the internal crystalline structure to handle extreme torsional stress in its final application. In another section of the facility, raw circular blanks wait their turn for heavy modification. The cold, raw steel is far too hard to shape at room temperature, requiring a dedicated thermal and mechanical cycle. The heavy industrial press stands ready to deliver hundreds of tons of shaping force. Heated back to a highly plastic state, the circular blank is loaded into the press. The heavy iron dies clamp down, locking the piece in place for initial forming. This clamping pressure prevents the metal from warping or curling as it cools. The operator makes vital mechanical adjustments while the metal is still malleable, ensuring the piece sits perfectly flush against the forming block. Once cooled and hardened, the rough circumference must be turned down to an exact diameter. A high-torque lathe spins the plate at high speed, while a hardened carbide cutting tool strips away the outer layer. This subtractive machining process aggressively peels off ribbons of waste steel, revealing a perfectly concentric edge that meets strict dimensional tolerances. Next, the blanks are brought to a localized forging station to create mechanical gear teeth. The intense heat softens the steel just enough to accept the heavy impact of a custom forging die. With a single, massive strike, the press stamps a series of serrated ridges into the edge. Forging the teeth rather than cutting them preserves the continuous grain flow of the steel, making the final gear vastly stronger and more resistant to shearing forces under heavy loads. However, this brute force impact leaves behind a rough, raised burr of displaced metal around the rim. To fix this, technicians use high-speed angle grinders to manually dress the edges. Abrasive discs smooth out the sharp imperfections left by the press. The resulting piece is a heavy-duty, interlocking mechanical component built to endure constant friction. Unprotected steel will quickly succumb to rust in harsh outdoor environments. Inside the ventilated spray booth, The finished gears receive a heavy coat of industrial enamel paint. The aerosolized blue mist adheres perfectly to the freshly ground surface, creating a vital protective barrier against moisture and chemical corrosion. Hanging on racks to air cure, the glossy finish visually transforms the rugged iron into a standardized commercial-grade product. The foundry operates on continuous cycles, constantly feeding new material into the flames. A massive steel grate is shoved into the roaring furnace, where extreme temperatures rapidly compromise its structural integrity. Within minutes, the solid steel completely liquefies, yielding a blinding flash of pure thermal energy. For large-scale casting, manual ladles are replaced by a massive crane-operated crucible. This heavy-duty vessel holds tons of liquid steel, requiring mechanized assistance just to tilt it safely. The crane operator must perfectly align the spout with the waiting molds below, controlling the flow rate to prevent dangerous splashing. Pouring too fast can trap air pockets within the cast, while pouring too slow allows the metal to cool prematurely in the runner. The sheer volume of molten material being transferred illuminates the entire factory floor, a controlled deployment of overwhelming heat and weight. As the liquid steel is directed into long parallel channels, it rapidly begins to solidify into structural bars. Technicians carefully guide the cooling ingots onto a resting rack. The sudden exposure to the open air forces the metal's internal structure to lock firmly into place. To produce continuous lengths of rebar, the heated billets are fed through receipts of automated rollers. Each stand in the conveyor system compresses the steel a little further, simultaneously reducing its diameter and increasing its overall length. The material exits the final die as a glowing, flexible rod moving at high speed. Because the metal is still incredibly hot, it behaves more like a stiff wire than structural steel, sweeping across the factory floor in wide, dangerous arcs. The operators must use heavy tongs to manually guide the leading edge into the next shaping die. This continuous rolling process ensures uniform thickness and adds essential tensile strength, preparing the steel to reinforce concrete structures around the world. In another corner of the yard, massive rusted ship chains are aggressively dismantled. An oxy-fuel cutting torch slices through the thick steel links, melting a precise straight through the oxidized metal. These heavy marine components provide an excellent source of high-carbon scrap for specialized forging. The severed chain segments are reheated until they reach a highly plastic state. With the steel glowing bright orange, an operator places the blank under a heavy mechanical hammer. The aggressive, repetitive strikes begin to compress the thick block into a tapered point. This specialized forging process packs the metal's grain structure tightly together creating an incredibly dense and durable tool piece capable of surviving heavy impacts. To refine the geometry, two workers collaborate to position the glowing mass beneath a precision hydraulic press. The machine slowly crushes the hot steel into a sharply angled excavator tube. Forging these heavy-duty digging implements requires exact timing. If the metal drops below its critical forging temperature, it will resist the press and potentially crack under the immense load. Every strike solidifies the piece, guaranteeing it will withstand the extreme friction of tearing through solid earth. Hours later, the focus shifts to a vastly different metal, aluminum. A continuous stream of liquid aluminum flows smoothly into a series of rectangular ingot molds. Because aluminum has a significantly lower melting point than steel, the process is cleaner and lacks the violent sparks of the earlier foundries. As the conveyor advances, ambient air draws heat away from the molds, and the molten liquid rapidly solidifies. The transition is highly visible, shifting from a glowing, mirror-like liquid to a solid, matte silver finish, from rusted, discarded scrap. To these perfect, standardized blocks, every station has added one irreversible step. The product is the sum of 100 small precisions. Tomorrow, the line does it all again.